Windows 啊，不 compatible 的。天好，我今天有 compatible，今天还可以。Hello. Okay. So please have a look on your quiz. I already marked it. There's something very obviously wrong one. Please don't write it again. For example, this one. Uh, so let's say you want to say that these two are homotopic equivalent. Okay, then by contracting the subspace, you cannot collapse x1. Right? How do you collapse x1? Okay, so this is not what you should do. But there's one way to go from here to there by attaching map. Okay, by attaching map you can do it, but cannot do by contractible subspace. So you could like attach your map like this, like slowly push your S2 around this S1. This is done by attaching map. Hmm? Is it possible to go between these two by collapsing subspace or not? Let me think, huh? Is it possible? Can we contract any? Yeah, you don't really collapse. You can't really collapse any subspace, right? To get between these two. Okay, but you cannot collapse x1. Otherwise, if you can collapse x1 means what? The fundamental group of x1 is just trivial. But we've spent the whole lecture proof that it is that. Okay, or you can use attaching map. You can do it. You can use attaching map. I don't think you can collapse any. Well, so do you know how to write down the deformation retract between these two space or not? You know how to write down the map? Oh, yeah, so how do you write that down? Oh, no, I'm asking about this. So a line with a why is a line? So I'm asking like why is a line? How do you write down the homotopy? How do you write down the deformation retract? Maybe choose this point to be a point on any point on this line. Huh? Ben, what do you mean? Mm-hmm. Then? Uh-huh. Answer? L, not T. Yeah. Okay. Oh. Uh, well, I guess well, let's take this as the star here. So your homotopy should look like this. Right. So this is the homotopy between the point and the identity map on the line. Yeah. So this is the homotopy you want. So this homotopy is also growing homotopy, kind of growing towards the whole line. Okay. Another thing is, I think Xiaoyue asked me about the semi-direct product. Mm, well, so if you look at the website I put on in the Moodle week, last week, I think, last week, I already put on the Conrad semi-direct product. Okay, or another semi-direct product notes here. Okay, so by definition, right, a semi-direct product is just let me see where's the definition. Is actually just should click this. Okay, okay. Here, just where's the semi-direct product? Yeah, we said that. Yeah, so the semi-direct product definition is this. That's all. Okay, G intercept H is 1, and then G H is P, and then one of them is normal. I think for product, both of them have to be normal, is it? Is that right? For product. Do you still remember the just one of them? Then what's the difference then? If we weaken the definition slightly, also already weakened. So the original one. Go up a bit. GH is P, GH also P, and then G intercept is 1. Hmm. Wait, precisely this one is a good one. Yeah, both of them have to be normal. Both of them. Both of them. Yeah, need both of them to be. But semi-direct product, only one of them is enough. Okay. So this is semi-direct product. But the semi-direct product that I mentioned last time was you can define a kind of multiplication to make it different from the product. Okay. So that's another question, whether you can realize this semi-direct product using a multiplication method. Okay, that's another question. Does it make sense? Okay, first of all, we just split it like that. Okay, we use the kernel, we use the image to split it because kernel is always normal. So you can always take the normal subgroup, then kind of take this external product and with your core domain, and then to get back your core domain group. Okay, but what's the multiplication that make it isomorphic? That's another story. Okay. Define depending on what group you have, and maybe depend on the homomorphism. Okay, so this the one that define using the multiplication one is in this Keith Conrad here. So if you fill it in, then where's the section? Let me find it. Yeah, so here also got definition on internal product, the external product. Yeah, and then yeah, so this is motivated. This is the motivation why we define semi-direct product. So here, this one. Okay. So if you have this kind of action on K on the automorphism of H, then you can use this to define the product. Okay, so you can see that on the K side, right? K is the normal guy. K, I think K is the normal one. Okay, so K you just multiply, but there's a action on K on the H. Okay, when you multiply the two. You forgot? It's the place where we the place where we when we discuss about free product. Yeah, free product. Yeah, when we discuss free product, when we want to see what's the Z free product with Z. Oh no, Z2 free product with Z2. Yeah. When we try to determine what is this is Z semi-direct product with Z mod 2. Okay. Okay, and then this is done. Previously was done. Okay. So from Wednesday lecture, right? You should notice that we should see the universal cover or the simply connected covering space as a set of equivalent classes of path. Okay, set of equivalent classes of path. So every point, right? Every point is determined by what? Every point is determined by the every point. Okay, so every point in the universal cover is a homotopy class of path, which cover an endpoint of that path in the base space. Okay, still remember or not? Now let me write down the definition. So what's the covering map on this universal cover here? So you take the path, homotopy class of path, and then you send it to the endpoint. Okay, you want to see some examples maybe? So how about let's look at our x1 example. X1 which x1? Okay, so here is A, here's B. Okay. Let's draw semi simply connected covering space. Okay, not big enough. Let's draw bigger. Okay, I think let's go to this level. Okay, go up a bit. And here. Here. Okay, so let's choose this A, choose this B. Okay, so let's say you walk around A, right? You walk around A. So start from this base point here, maybe choose the base point here as well. So this is not tilde, here is not. So you walk one round, okay, you move, moving in that direction, in the following arrow direction. So you also walk one round here. Okay, make sense? Okay, so how about what's the next where you want to move? What do you think? You want to go B? Okay, so maybe we fix a direction on B as well. Then maybe we can move along the direction of B as well. Then our B is always a vertical one. So in this case, you will end up at the another junction here. Yes. Okay, so if you go the other way around, okay, if you go the other way around, then you will move downward. Okay, does it make sense? Okay, so you can see that this green path here, okay, will determine this point. This path here. Okay, so the endpoint of this path here will determine by the path you take. Okay, so this is so let's say let's call this gamma. So here the whole thing here is gamma. Okay, then this green path here will be homotopy. Okay, makes sense? Okay or not? Okay, so if you can see from the base space picture, right? No matter how you look, you are still at this two circle. But here, no matter how you look, you will go to different level. So covering space is like I draw out the map that the possible path that you can take. Yeah, so covering space is like drawing out all the possible. So distinguish every different homotopic path you can take. Okay, no? At the bottom, you just see that, oh, you're just looping around there. But at the top, you can really see that. You see, if you go to the left, it's going up, go to the right, it's going down. So these are clearly two different directions. Okay, no? So covering space is like, okay, is what?
很自由的
Zero.
How do you? The
Yeah.
space is not in any shape. I can go wherever I want, but with a certain action.
How do you interpret? Zero. I don't understand. I mean,
You understand?
not really, because no matter how you move here is also how you move here actually. It's just that
Yeah, but in current space, those actions.
also not that free, right? Depend on what the covering space you have. Yeah, you can do what the covering space you want. But later we will see this loop as action. And later we'll see it as an action on the fiber of this base point. Actually base space as well, because you can move every point already, okay, not just the base. But yeah. Okay. 什么又中毒啊？
哎，你整天讲拉，我靠！
很顺畅呢。Okay, next, let's look at few ways to classify covering space. I mean, classify covering space is a way to jot down the different type of covering space. Okay, so it's using permutation. Okay, SN. Let's look at some examples. Look at some examples. Let's look at some motivation here. So first is consider the three-sheeted. 听到sheet 是不是想大便？ Three-sheeted spaces of x1. Okay, so there are three ways to draw this. Okay, the easiest three way is you just draw like 1, 2, 3. Okay, the pre-image is like, so well, I mean, you can build a, I think it's easy to see what's the P you have to define, right? Okay. Maybe you send this 3 point here to the same base point, and then you will get the whole full circle. Or you can make two of them meet, maybe like this. So you make, so okay, let's use this to draw. So maybe I can tell you a bit of grading. Okay, so how about let's break the first two. Okay, let's break the first two. So let's break this two. Okay, this is also three-sheeted covering. Okay. Every point have 3 pre-image. So there are also 2 points here. It's just one top, one bottom. Another way we could do was we break 3 of them. So if we break 3 of them, this. Okay. So from this picture, right, I think from what I have trained you in AA1, right? Can you see commutation here? Huh? See commutation, right? Okay, so if you chop the top and bottom away, this is identity. Then this is the commuting 1, 2. And then this is like 1, 3, 3, 3 to 2, 2 to 2 to 1. Okay? But this is exactly the action you have if you take the loops acting on the pre-mesh. Acting on the pre-mesh of the base point. Correct or not? Okay. So let's say let's say this is the covering space of x1, right? Okay, just draw x1. Okay, so if you take this point, okay, you can consider a pre-image of them. Okay, you can consider any pre-image of them. And then you consider a loop around this base point. Okay, you consider a loop around this base point. Okay, so if you leave this point here, for example, in the first picture, if you leave to the inner circle, then this loop will just bring your point back to itself. Okay, similarly, if you leave to other pre-mesh, is the same thing. It's the same. Okay, it's the same. If you leave to any of them and then you draw a loop, the leaf of the loop, if you're gonna go back to the same pre-mesh. But this is different, if you use the other covering space. For example, if you use the second one, okay, if you leave to the inner one, well, you go back to yourself. But if you leave to any one of the two of the braided part here, and then if you loop around one round, so you loop one round like that, then you will go down to the other pre-mesh. You'll move to the other pre-mesh. This loop will move you from one pre-mesh to the other pre-mesh. Okay, similarly, of course, this one is come with a direction. You need to add in your direction. But similarly, for the next one, you will move, for example, for the first, I don't know how you call which one first, maybe 1, 2, 3, like that. Okay, you will move the first pre-mesh to the second pre-mesh. Like that. Okay, if you move again, okay, if you move again, loop around at the bottom, you lift it up, you will move to the third one. So if you loop twice, meaning you will move your pre-mesh twice as well. Okay, but twice going to the the third pre-mesh. Does it make sense? Huh? 啊，一开始什么是一开始？其实一开始，EIT 啊，EIT that one is simply connected。怎么有这样重的声音？EIT the one that we considered last time was infinite shaded. Which one? Like what? You cannot connect them right because they are two different endpoints. So every loops will bring you either up or down, depend on your orientation, to another pre-mesh. Does it make sense? 搭电梯 yeah exactly 啊 yeah 什么都要一样第三个一样第三个 the third one will come back to the if you move like 3 loops you come back already but at the bottom you cannot come back one unless you turn back 我觉得是大个 what do you mean 什么叫很多层什么叫很多 I mean it's a different covering space already it's a different covering space this one is 3 sheeted. Okay, is the simply connected one is infinite level. And so if you move in positive direction looping, then you will just keep going up the pre-mesh base point. Then if you decided to turn back, you need to go down the level
That's what the top universe.
Yeah, yeah. This one. Yes. So if you want to draw it like straight line, right? It's better that you did not where is your base point and then what's the full turn, no? What's the next pre-image, no? Depend on what's your P. Maybe you label by 0, 1, 2, 3, or you label by 0, 2 pi, 4 pi like that. Depend whether you use e to the it or you use e to the I 2 pi t. Yeah. Okay, then either you use 2 pi to label or either you use 1 as a unit. Okay, clear? Clear? Okay. Okay, so let's look at some example here. Oh, where's my So if you look at this example here, okay, so can you determine like for this covering space, what is this loop are doing or not? The leaf of A. Here although they write A B here, I really you should think of it as the leaf of A or leaf of B. Then these correspond after mapping is B or A. Okay, so these are the leaf. So if you look at A, right, what does the leaf of A do, for example, in the first covering space? You just send the base point back to itself, back to itself, back to itself, back to itself. But B, you can go from one base point, one pre-image of base point to another pre-image. And then you send back. Or you send back and forth. So it's one, two. Okay. How about number two? So you can see that A and B no longer loops inside covering space. So you can also see that they connect the two pre-image of base point. So if you do A to the pre-image of base point, you send to another base point, and then you do it again, you send it back again. So it's like a transposition. Okay, and then more interesting one maybe is 5. Five. Look at 5. Okay, look at 5 here. So this is a computation of 3 points here, so it's actually S3. 哪一个圈圈？什么意思嘞？哦，no, right? Because these are wedge point. These are wedge, so they must like self-intersect. These are wedge point, so they must self-intersect here. Just now we don't self-intersect, huh? 哪里有波浪？ Huh? Yeah, kind of, yeah. Yeah. Mm-hmm. Because I
Are they in S3?
let me see. Wait, let me think. Is there any problem? No problem, right? I permute 3 things, right? Should be S3, right? So I'm just saying that consider the group generated by A. Let me see. Is it possible or not? I think something wrong here, is it? I think it's not S3. What is it then? You can move 1 to 2, you can move 2 to 3. Oh, it's S3 actually. Okay, so I mean like because these are 3 different leaf, right? These are 3 different leaves, so maybe this one should be A tilde 1, A tilde 2, A tilde 3 like that. And then these 3 things build out S3. Correct? Yeah, because A is transposing between 1 and 2, and then 2 and 3, 3 and 4. 3 and 1. Go back. 1 to 2, 2. Yeah.
Think that it just you treat the
Mm.
3 copy of the point element action.
Yes. You use the loop to act on this point. The leaf the leaf of the leaf of the loop will act on the pre-image of the base. Yeah. Okay. Yeah. So this notation actually not standard. But I think you should know what I'm trying to do. Maybe I write like this better. Because they don't label the A or the A, so they are kind of degenerate under this writing, but they are not. They are different lift. Okay? Make sense? Okay, so maybe if you like, A1 tilde here is 1, 2, and then A3, A2 tilde here is 2, 3, and then A3 tilde here is 1, 3, like that. Okay? If I label the base point as 1, 2, 3, the pre-image of base point. Make sense? You do a loop around this base point here, then you go from 1 to 2. Using A2, A2, A2. But I even I write like this, right? Actually, it's not quite standard also because it's really depend where you start lifting your thing. Okay, it depends. So if I put 1 here, meaning I should start my lifting here. Okay, if you lift other place, then you should like relabel the thing. Yeah, no, you should relabel. Yeah, standard 的 way。我不觉得嘞。
Still, I'm asking you
Mm.
just do 1, 2, 2 students.
Mhm.
What is the other end? Maybe like what is what is the
What do you mean?
not necessarily contain other element like one.
Okay, so depend on how you lift it. So I guess depend on how you lift it, and then
And also the
yeah. Mhm.
one
Mhm.
that you
Mm.
It's
Let me think.
so is it
Yeah.
just
1, 2. So wait, so should I write like A is 1, 2, and then A square is 1, 2, 3, and then A cube is identity, like that.
I think it's 1, 2,
1, 2, 3, what, and then?
because it turns 1 to 2,
Mhm.
2 to 3, and 3 to 1.
Oh, okay, sure. Oh, okay, sure. So what did you say again? So A
A is
Mhm.
1, 2, 3.
A is yeah, sure. I think you are right. Oh, okay. So okay, sure. I think I get what you mean. So you should check what A does to 1, 2, 3, and then write down. Okay, yeah. Okay. Yeah, I think this is not quite S3. Okay. Yeah. Okay. I think you're right. Yeah. So basically, you check the A on the different pre-match of base point, and then you decide what's the permutation.
projection
嗯哼
三个一样点。
Yeah, 3个都是一样点 yes, exactly. So, and in the base point, you cannot really see anything, but on the lift, you can see something happen. That's why this is interesting. Okay, in the base point and base is not interesting. So on the actually these are what we call the because you got these pre-image at every point. So these are the fiber. If you remember the inverse image are the fiber. So we actually attach a fiber at every point. And then on this fiber, right, it's different from what we see on the base space. They have some swap inside the inverse image. And then this makes things interesting. Okay? Does it make sense? So on the base space level, you see things the same, but on the covering space level or fiber space level is different. So you cannot just see things from the surface. Understand? If you put different covering space, it is different. Yeah. Okay. Understand or not? Yeah. Huh? Huh? Hmm. Huh? Number 5, yeah.
It looks like two.
Yeah, three-sheeter. Three-sheeter. What do you mean 2, 3? Three-sheeter?
Yeah.
No, it's just 3. Because B have to have 3 pre-match also. A have to have 3 pre-match. And then base point have 3 pre-match. Everything has the same number of pre-match. It's a proposition. 没有两个，那里两个，什么叫两个？这整个东西是一个 tree sheet 的，每一个点都有3个 pre-match。Okay. And then the rest you can try and figure out. Then I think this is S4. This is maybe. I think B is the other way around, right? If A is 1, 2, 3, 4, B is something else already. But I think B is 1, 4, 3, 2. Okay, and then you can try and figure out the rest. Okay, so how do we yeah. Say again. The action. Yeah. So we're gonna make this formal. So the action of pi 1 of x on the fiber, okay, exactly the image of x naught is defined by the homomorphism phi from pi 1 to proper potential of inverse x naught. So how do we define this? Okay, so this is the very special definition here. So you take a look. Okay, you take a look and then you add on the pre-mesh. Okay. But you maybe you see that a very weird here. Why you add on the endpoint and then go to the starting point? This how we go from the starting point to the endpoint, right? Okay, but this is just some formalization such that when we compose path later, okay. So when we compose paths like this will respect our composition, respect the path composition. So let me write down what do I mean. So this is to make sure that L of gamma star gamma prime will be equals to L gamma on L gamma prime. Okay. If you do the one we do just now, then this two position will swap. It doesn't matter, but we just keep it so that we follow respect the order of path concatenation. Okay. Does it make sense? Oh, question? Okay. No, just some. Okay. Okay, so I recommend you to verify this. Okay, then you will know why we define like that. Okay, why we define the sending the terminal point to the starting point. Is this injective? This injective. I don't think so, right? Because yeah, you could add the same, or you could look around a few times, then come back to the same. Okay, might not be injective, depend. Okay, so this is where the Sn coming out of permutation. Okay, because Sn is just bijection between n elements. Because in this case here, do we need to fix it is finite? Not necessary. If it is finite, then it's just a bijection. But then, I mean bijection between n elements, but it could be infinite otherwise. If it's infinite, maybe you cannot write down the full computation. Yeah. Okay, so there's the next very interesting definition here where we can rewrite our covering space as actually a real product space. Okay, quotient out by some equivalence relation. Usually product space is easier to identify if you know the two product space. Okay, instead of a whole covering space, I mean the whole space. Okay, we kind of like decompose this covering space into a product space, but with some equivalence. Okay, so when can we do that? So as long as your X is path connected, locally path connected, and semi-locally connected. So this is to make sure that we have a universal cover for it. And if you take any covering space, then we can build. Okay, we can build this covering space actually by the universal cover. Okay, so what we're gonna do is we take the universal cover, okay, the set of equivalent class of path, and then cross it with this fiber. Okay, so this fiber is just your base point. Okay, so for every inverse image of base point, you attach a universal cover. So let me think. So this hash is depending on P. Okay, so what kind of example you want to think of? So maybe so let's look at our example of x1 wedge x1. So let's say h1 wedge s1. So just now we got an example, right? So maybe something like this. 3, 4, something like that. Okay, maybe I shouldn't draw this. Okay, let me draw a proper one. So this is A, and then this is B. Okay, and then we know that we got a covering space like A, and then B, D, A, like that. Okay, this is the two sheeted covering. And then we know that the universal cover of this guy is like that. Okay. Okay. So now what you should imagine is I'm trying to take this infinite fractal here. Okay. Make it something similar like this. Isomorphic. So somehow you need to, you see, there's like infinite edges going out, right? Somehow you need to identify them. Okay, you can do something like this. Okay, so how you do that? So based on this construction, right, you should take each piece of universal cover, like put one universal cover here, put one universal cover. And then you need to identify until you look at. So what's the identification you should do? It's actually not obvious from this relation here, but later when you identify something, then you recognize that this is what you do. Okay, so let's see what you need to do. So basically, because your universal cover, right, I mean this space here, one universal cover consists of homotopy class of path, and then the leaf of S naught. Okay, so what you need to identify here, basically for any loop, okay, any loop inside your Taiwan extract. So you concatenate with your gamma, and then you take this loop, add on your S naught here, and then you identify all of them. Okay, as long as your loop, sorry, as long as your path is anchored by a loop, they are the same. At the same time, the base point is affected by this loop. Identify them. Does it make sense? Does it make sense? Hmm? 正好对，不对？I mean，你现在不是看得懂，但是你知道他做了什么？不，你可能你的不懂，可能是不知道为什么他这样做，是不是？还是你是看不懂这个 symbol？看不懂这个 symbol？这 symbol 就是 like you compose the loop with your gamma and then take the homotopy and then you take the loop add on your x block，对吧？很简单，可以算完这些东西，然后你就所有的可能性都是一样，就这样吧。只是为什么我们这样子 define 它，可能还不知道为什么。
应该
说说看。
在你 current space
Yeah，
里面的 A 会有两种，
A 会有两种的哈。
然后你 compose 它会代表你走到那条路然后你的 base point 就可以去到第一层，所以我们要 add point。还有一次，你那个让它like maybe 在这里，如果我们走 A，走 A 走，那我们就去到一个点啊，对不对？
要同一个点。
因为我们走 B 要去到另一个点，
要走 B 去到另一个点。Yeah， sure。
然后这个 B 就是我们的那个我大概知道。然后我的 base point 这个换成
Yeah，
我就 act。那我觉得看那个 infinite 的话，应该更加好看一点。
哪一个 infinite？
无限的。
Yeah。
走了过后，然后一样的点就换成不一样 level 的地方。就把然后我们把这些东西都锁起来。
你能够直接从这边看得出跟这边的关系啊，这个过去。你可以感觉是有两片 waffle 在两个点上面。但这个 waffle 怎么能够来？这个是什么 ？This one actually defined based on your P, right? Just now the action we define here actually based on your P. Okay. So for example, what does your if you want to ask about lambda, there's two lambda you need to consider here, right? There are actually A and B. You need to consider. Yeah, for the rest is like use of these two. And then if you look at the pre-image, what does this A do? A should just send S naught tilde back to S naught tilde. But he will send to another one. And then you should somehow think like after this identification, why you could have this kind of be joining that two fiber. Why? I don't know. Maybe you can try think about it. Yeah. Gamma theta is the universal cover. Gamma bar theta. Sorry. Gamma bar theta 哪里有？Gamma bar theta 我在做什么哈？哦，is you invert the you transverse backwards first and then you lift. Correct? Yeah. You transverse backward and then you lift. Because I'm trying to like convince you that we actually have a starting point and an ending point, but try to cheat you. I take the end point. I take the terminal point to find the starting. Okay. Yeah. So it really is just permutation of inverse image of a point. Okay. Does it make sense? Yes. What's L lambda? L lambda is defined by this map here. It's a permutation, yeah. It's a permutation. Yeah, it's a permutation. It is a loop. Depend on what's the split here, you will send to the
你上面应该也是 max two，为什么上面2？
to the group of
The permutation is from gamma minus 1, gamma 1 according to gamma
Yeah.
two.
Yeah.
The permutation 不是同一个 set 上的方法。
这个是 set 啊，这是 inverse image
Permutation should the start and the end should be the same set.
只是变，
Oh, because our gamma is a loop.
你以前干嘛？
啊干嘛也是啊？什么？哎呀，也可以，但是就是可以，但是就可以啦。对呀，你要的话可以，但是就是可以。如果你要我翻 x not， I think 也是可以。Yeah. Yeah. But 有两个 convention 嘛，你可以终点去起点或者起点去终点嘛。我们选终点去起点 ，because if you try to verify this， 你翻终点去起点这个东西才会 work， 不然的话你这个要算。如果你是起点去终点，你可以 try to compose 这些。什么？因为你进到我们这个东西就是反的，其实我们把先做的东西放在前面，后做的东西放在后面。因为我们的 path concatenation 就是已经反了，其实跟 function composition 是反的。但是 on this side is a function composition， 不是反来反去，是这个世界就是有某一个方向，但是有些东西是 work 另外一个方向，所以我们就要用另外一种方法去记录它。
有人打通，
有，其中一个就是我的老师啊，我的老师啊，他先问我们先，哎，你们要 define 哪一个方向啊？你们 composite of function 要哪一个方向？对呀，有的。Okay, how about we don't go through this long proof lah, but at least show you why this identification makes sense. Okay, I will briefly discuss why this identification makes sense. Okay, how about let's take a break now. Break until 3:05. Please have a look on your quiz, because how much you get, and check what's your mistake. Please don't make it inside your midterm.
莉迪亚跟我说让我多问。
我这个，这我还不知道是什么，就记在那边。会怎样？
莉迪亚让我不知道你还比较这个说。
因为我做菜嘛。我一考完我就想到，哎，我考 3S 了。对呀，我也不
S1。
哎，算了。
我的那个线的意思是想要把那一半连到那个 S1 上。
对呀，那个也是 attachment， 不是 collect。
那个两个你根本就 control 不出来。
哪一个？哦，对，应该是不能，应该是不能，应该不是不能。所以你只能够用其他方法去他们那边。
去年啊，回进的时候就要还。
因为我们是要 collect 嘛，所以你要选可以 collect 的方式哦。但是你要如果可以 attach 的话，就可以过去。
我是盯着那个定义一下子，
哪个
最后一个就是那个加呀，下面的
action，
这个
黄色，这个。
哎呀，我要是听这个。
我突然觉得这个对我来讲很自然。
是哪一个 part？
这个东西。
忘记了这个什么意思是 difference base。
你不能够，这两个是长不一样的东西。你是讲这个放进去就是变它了，是吧？放进去就变它了。
转进去啊？
转进去是不是？
I mean 我的意思是，
这怎么会叫 move the loop 呢？
我也不知道。
你是讲它在被推进去这样哈？
哦，
就是刚才那个一个你包出来或者一个，这个应该不叫做 move 吧？通常 move 只是来就这个 loop 来 loop 一下。
push in，push in。
English。
我们叫 attachment 了。对 ，OK。我以为你是直接丢进去，那个肯定错。 嗯，
还是很
但是要用 attention map 哦那个东西，
诶，我懂了，我看懂了
你，看懂是啊？
看懂了。
看懂是啊
为什么这个可以看懂这个
？OK，你看看，
啊，这个 OK，我下面
你看看，
这里是
这里 OK，这里的 covering space 和这个 covering space 应该不一样。这里是有 infinite sheet 的，
肯定啊
只有 two sheet 的。
嗯哼，
所以如果我们这个是 A，然后这是 B 的话，
那是什
对
么？
那如果我们先走 A，我发现到
，lambda 是一个
好像
吧，
这个 A
，lambda 怎么可以变成
X 这个转来一圈，我们会在这里，
我们上面就是把它是在那个
然后再走 B，
那个
走 B 我要去下一
是
层，
basic 路，但是我们这一个
就是走
上去
A，
以后，它可能
走 A 我要去下一层。
我们这个是在 covering space 的吗？
什么
covering space 哦，那不是
所以
对啊，
在 covering space
啊，
对啊，
其实就是来
是
其实
gamma 是 covering space 的路，
比较奇怪的是，
gamma
在这里我走一个 A，
space
我是怎样会跑去下一层？
gamma 是路吗？
应该是你有2片嘛，对不对？有2片，对不对？OK，
没有，
然后
也是 base space 里的
这一片
universal cover space 里的 element。
这一片里面是
它是 universal 的 path
可能
base 的 base
所以是里面的一个 group，然后在 universal
我应该要讲放
是 universal
这边是 SE 啊，这是 SE，
space
对 S，
里面的 element，
然后 SE 配了8，
哦，
and then S2 配了2，不对？然后怎样讲呢？
element，
你是什么意思？
说来明来看这个嘛，OK，这一个嘛，这一个配上这一个就是这里面的所有的点了，对吗？这个配上这个是所有里面的点，然后我要 identify 这边有很多点，对，很多个涨降的东西，这个是 S1 跟这个是 S2 跟这个，然后我怎样对联？对联的话，只要有一个 gamma add on，就是我看它的 orbit 啦，对不对？我看它的 orbit，其实这个就是 orbit 来的。说我 orbit 有什么可能性呢？我可能有可以做 B，可以做 A。OK，假设我考虑这个点呢，这个点要连去哪里？比如说这个是 A 啦，这个走 A，走了 A，说我走 B，OK，我走 B，说 B 走在 A 上面，C 下面。所以我走了 A，我再走 B，OK，是往上走。但是我不是这个点哦，我是这个点，OK，所以是说这个点跟这个点在一起，undo 它的多走 by loop 的，而且还要被你的这个 base point 控制。因为你不是把这个点跟这个点合在一起哦，你是把这个点跟这个点合在一起。对，A 走了过后，A 走了过后啊，继续 A 走了过后
用走 B 嘛，
走 B 啊，对，走 B，
丢掉。
嗯，我想一下，我们把这一个点跟这一个点连在一起，所以全部 defer by 一个 loop 的东西，我们都把它 identify 在一起。
没有走， sort of like
嗯
sort of like，我现在在这一层楼，
对
在 G
对
109，
对，
刚才讲我上去109的话也是一样的，
你用 loop 走的话，
从楼梯走上去，
对，
我还是在
反正它这里路就是
对
你走完一个路，你就上一层了。
对，
然后
但是
你干嘛是
我还不能够直接看为什么是长这样啊。我知道是这样 identify 了吧，就很丑。
就是这个两个
是这样
covering space 的 starting point 是不一样的嘛？
这两个的 starting point，那我们就选一样的啦，我们选一样咯，我们选一样。
I mean 你这个你选 S，
哦啊，wait，let me，no no no，不是这个意思，不是这个意思，这个的意思是 like 你懂 R2嘛？就是每一个点有一条线嘛，对不对？这个就是一个点上面有这一撮东西哦。I mean like，
哦，
啊，
这一个点上面有这么大力的东西，
对对，
这个是
对，
这一个点上面，
这个不懂哦，我不懂怎样
这样
去讲这个，
猜它，
不是，问题是这个粘了过后，我不知道怎么去，可能我还没有想到，可能我想到我跟你讲，but 有 proof 是 like 他们是 isomorphic 啊，但是那个 isomorphism 是蛮简单的，其实上去 endpoint 吧，
哎，刚才讲
呀
到是
呀呀，
什么叫做这一个点上面
嗯，
会有对补东西，就是这个意思。
因为这是 product set 嘛，所以你的 F 是你这个 K 是两个东西嘛，对吧？所以这个 set 其实就是等于 x tilde head cross with 一个东西 union x tilde head cross with 另外一个东西，不是，
这个是那个
嗯
那个
，product set，
我是讲这个 x 八，然后
嗯哼，
x
嗯哼，
x 八
嗯哼，
x 是那
嗯哼，
个
嗯哼，
把它 send back 回来，然后再 dig 回来，是这个
哪一个？这个啊
这个的，这个
这个啊，这个啊，
哎呀，
这个是那个 universal cover
嗯，
啊
就这个是吗？
for S1 which S1 是这个啊，嗯
哦，OK，那这
，OK，
个的话是另外一个 universal cover for S2 的。
它是同一个 universal cover，只是说 like 一个是跟着 X1，一个是跟着 X2。
哦，
所以有两片这个东西，然后我们要把它粘在一起，粘了过后它会 isomorphic 去这个，或者 homomorphic，
把这两个连在一起，
来粘在一起，用这个罢了，就可以粘住这个东西了。
这样这个实际长什么样子？嗯，
这个，
这个 L，
然后 lambda 只是这里面的 loop 罢了，可以是 b 啊，可以是 b square 啊，可以 a b 啊，这样，可以 a b inverse 啊，也可以，全部
这样子这个
很simple，
原本
你不可以走一半 b 罢了，那就不可以，你一定要走个 loop，嗯，
这样子的话，这个就是这也是路吗？
哪一个？
就是这个
这个啊，这个不一定，这个不一定，这个只是 path 啊。
好，
因为这个是 S Q 达里面的点，S Q 达 head 里面的点是 homotopy class of path 而已，也有 loop，但是也有 path，所以你看这些是 path 吗？呢 path，OK，
可以啊。哦，
因为你出去回来就是个 loop，
是，
但是这个 loop 是 trivial 的了，
这个是有，
什么？
这里全部
嗯
走这边到这边的话，
嗯
就是每一层啊，
嗯
就走回来走回都会有5000个个
嗯哼，
那个 works point 哈，就是一样的，5000
怎么说
个就是叫我 b
？Three image 啊，base point，three
呃，
image，
它的 image 是那个 X1，
呀，
是啊，有5000个
对对对，
，OK，
嗯，5000个，那这些全部都是
这样还可以走无限次，
可以啊，可以走5000次，
无限
可以无限。就像你在下
无限的
面无限次走啊，对，你可以在下面无限走啊。
变得 path，这样子的话，还要讲 map 去那个
哪一个？
用那个叫什么了lambda，就是一
对
分刚才有问到的，
对，
讲就是如果是 infinite 的话，
你就
去哪？
走了 A B A B A B
但是
A
还没有
B，
endpoint，
你的路会停啊，你的这个 lambda 会停啊，你的 lambda 会停啊，你不可能走 A B A B A B 无限 A B，那个不是一个 element 来的，group element 哪里有那样写的？我 group element 不能无限扯下去啊，我一定会停一个 finite 的 composition，finite composition 过后就是停在某一个点的
嗯，
确认是有没有认错。
呀，
比如说伽马，假如说这个点是 x0，
嗯哼，
这样子这个伽马呢可能就是这一条路，这个就是伽马。 这是
可以
prime，然
啊，
后呢
你可以拿
gamma
这
x
条
零，然后呢
S 这个 S0 tilde 是外面那个点来的，
x 零 tilde 是，
它是一个 coordinate 罢了，它是一个 coordinate。
对对，它这个 coordinate，我们
对
假设这个 coordinate 是在中
对
间这边呢。
对对
lambda 呢，就是假如我们讲 lambda 是从这一边到这一边，这样子 lambda gamma 就是一个从我拿这一个点冲过 lambda 把它印回起点，
没有，你应该
这里开始的这一条线。
哦，你是说反
是这样
着做哈？
我是讲我是想理解这一个和这一个在 universal couple 是长什么样子，所以它
可以
讲的是这一条
可以
线其实它是等于
可以
这一条线是这样。
可以，我们可以讨论呀，我可以讨论这个，我们一起讨论，可以，我们可以讨论这个，OK，我可以讨论这个，可以，我可以讨论
没有
呀，
OK
我现在讨论，OK，全部人不见了啊，在班上哦，还有 Rachel，
那两个就找了我，
没，
看到那个。
有空就找找哦，我挺闲的，我就是因为这样不写，OK，right， so okay, so let's give an idea on what this identification doing here. So let's use this example again to talk about it. So we got AB at the bottom here, the base, okay? And then let's look at some gamma, okay? So this gamma maybe is just this leaf here, A tilde here, and then paired up with some S naught tilde. So S naught tilde maybe let's fix one is x1, one is x2. So this is the piece with x1, this is the piece with x2. Okay, happy? Okay, and then all the leaf we pick is from the middle for easier discussion. And then what's this identification doing is, so if you look at the, let's say we take lambda to be p, be b. Okay, let's say we take lambda to be b. Okay, so what have we done? So what is B composed with this gamma here? So our gamma here actually is A. Okay, so what is B composed with gamma? Okay, so if you look at the x1 here, and then you move B first. Okay, actually, if you move B first, you should move up first. Okay, and then you move across. Actually, it's this point here. Okay, BA. But then what happens here was B. Okay, so if you refer, so this is the path you're gonna send to. Okay, but there are two choices here. I'm not sure is this one or this one. Okay, because you have to check what's your S not tilde. Need to check this guy here. This guy. So if this guy is S1, then this is the path. If this guy is S2, then that is the path you want to identify. Make sense? Yeah. So let's start with gamma. So let's start with alpha comma x1. Okay, see what we want to identify. So we already compute the path of B star alpha. Okay, we need to check what is lambda gamma here. So what's lambda gamma here? If you remember, we are sending the endpoint to the starting point. Okay. So what's the endpoint of gamma? What's the endpoint of gamma? So how do we leave gamma here? So we leave gamma to this point, x1. Then let's say we leave gamma to x1. Then the endpoint of gamma is still, okay, let me think. endpoint. So this is it here. So here is S1. Where should we leave this one? So now let's compute this. Compute this one. Let's compute this one. So how should we compute this? So let's write down first. So this is lambda of b star alpha. Sorry, lambda of b of x naught. Okay. So we need to determine what is this. So meaning this is acting on x1 in our case. Okay, but we know what happened. B will act on x1, right? B will permute x1 and x2. Okay, B will permute x1 and x2. So this LB S1 here must be S2. Okay, so what happened is you have identified this path, the blue path on the first one, to the green path on the second one. These two paths you identify. Okay, that makes sense. Okay, but you have to do it for all the paths. Meaning what? Meaning actually you look at the orbit of this section. Okay, orbit of this section on this product set, and then you identify the whole. I don't think it's why is it? Let's look at the looking. I mean, looking like this two-sheeted covering here. But let's continue first. I'll tell you what's the covering map. Maybe from there it's easier to think about. Okay, so how do we get the quotient relation? Actually is how we think about this map from this product set to S tilde here. Okay, to think about it, what we do is we also look at the endpoint. Okay, really the covering map from simply connected space or universal cover is just look at where it ends, where the leaf ends. Okay, so in the usual covering space, right, you look at gamma 1, but here you look at gamma tilde 1. Okay, because we are like covering the covering space, another covering space. So that covering space has a leaf of gamma. Okay. So this is picked, this is chosen. So which gamma leaf you pick depend on which pieces of universal cover you leave. Does it make sense? Okay, depend on which pieces of covering universal cover you leave, you send it to the leaf, the endpoint of that leaf. Okay. And then we show that the kernel of this map is that identification we have to make. Okay, so suppose that the two endpoint is the same. Okay, suppose the two endpoint is the same. So what could possibly happen? Okay, so suppose that the two endpoint is the same, and what we see was what we see there. Okay, think about it. When can these two endpoints be the same? When are they the same? When are these two endpoints the same? So you have a gamma, okay, you leave from S tilde, S not tilde, and then you check the endpoint. Okay, let's go it. I think the picture is here. The picture is here. So you start with S not tilde, okay, you lift it, and this endpoint is the same as another path that start with different place. This is the picture. Okay, this happen if the two endpoints the same. Then what you see from this picture here is this equation. Okay, how you go from S not tilde to S not. How you go from S not tilde to S not tilde. the S not prime theta. Okay, it's just doing one loop and then transverse the other loop. This is on the base point side. Okay, but then what? But then if you set this as your loop, okay, then the top definition is just what we have written down. Is a loop times your original part, and then loop acting on S not theta. But this loop is very special. Is one part composed with the other transverse of the other part. It is not a loop in the leaf, but project down to base space is a loop. You understand? Remove this tilde is a loop if you compose them. Why? Because removing tilde, these 2 points are the same loop. Make sense? Okay, so this is one direction. The other direction, yeah, so conversely, for any loops, you actually can check this is true. Then this is the only relation you need to take care. Okay, for the other direction, actually easier. Okay, no? No question? Actually, I think the most important picture you need to remember in this argument is the first one. So this picture you need to remember. Okay, this is the main picture that you need to argue why this is the only relation. Okay, so basically you are checking this point here. This is the important point. The connecting point here is important. Okay, the hash map here. Okay, okay. The next part is very difficult already. You want to show that this S rho tilde here is a covering space of X. This is very this is quite general topology. And then where is the homeomorphism? Returning to our algebraic extension of P, the mirror into hash is a bijection. So because we already quotient out the relation, so it becomes a bijection. And then you need to argue why is it a homeomorphism? Because the argument here is H is a local homeomorphism. Okay, then you can piece them together to become a homeomorphism. So this is the big idea. Okay, question? Got question? Question? So the key here is what's the covering map you are considering? Actually, it's just looking at the endpoint of the leaf of the path. That's the covering map. But maybe you need to show why is it a covering map. Yeah, that's it. So that's the hard part. Yeah, that's the hard part that I skip on. So basically, all of them are here. Okay, so it's subjective. Okay, but injectivity is settled by the identification. Okay, then how about we skip this? This one you can read your stuff. Two covering spaces are isomorphic if and only if the following commutative diagram exists. So that means it commutes with this is very interesting. Maybe this is something that can be generalized to other fields of mathematics. So two covering spaces are isomorphic if and only if you have an isomorphism on fibers. Okay, on fibers such that this diagram here commutes. Okay, this diagram means what? This isomorphism here will commute with the action of loops. Loops. Path or loops? Here gamma have to be the loops or path. Let me check. Oh, path, loop, because our action is pi 1. Okay, does it make sense? This is very important, or this is something that other field will be using. Actually, something is called like monodromy and stuff. Yeah. And then something called, what is the name? Very long time didn't read this stuff already. Group point? Not group point. What is that? Something transport. Not parallel transport, but what's that thing? I don't recall the name. I don't recall the name. Okay, next time if it's have chance, maybe I can bring out again. Okay, so you can try and prove this. Very interesting proof. Not hard also, but you try it out. Okay, so all together we have shown that, for example, on the n-shaded covering space, they are classified by the equivalent classes of homomorphism from pi 1 of x naught into Sn. Okay, so equivalent class here, it just differ by a conjugation. Okay, yeah, so this is for this part here. Okay, so for just now, we are just checking on the fiber of base point, right? Okay, so let's look at the general action on the covering space. Okay, so we'll define something called the deck transformation or the covering transformation if you have a isomorphism between covering space and itself. Okay, so actually it is a endomorphism. No, more than that, right? Automorphism. Okay, between itself. Isomorphism between itself. So automorphism of covering space is called deck transformation. Okay, so maybe you can think about why is it called deck. So just now you have a level idea, right? Go to different level. So deck is like different deck. 不同的抽屉. Okay. So let's see. So what are the group of transformation? So set of deck transformation form a group, I think is pretty obvious because you compose is still bijective, and then you're still sending to itself. So for example, what are the deck transformation here? You could imagine. So for example, the first one, the deck transformation of universal cover of S1 is that. Does that make sense? The deck transformation. So the automorphism between R is that. Okay. I mean, this automorphism here is quite restrictive, right? It's a homeomorphism, and then such that what? Homeomorphism plus what? Isomorphism of covering space. What's the definition? Yeah. So it's not a random automorphism. It's I think it's commute with the covering. Okay, commute with the covering. So yeah. You can only send the things within the pre-image of pi what? P1, P2. Yeah, only when they have like, but P1, P2 is the same here, right? So the pre-image of the point. You can only permute the pre-image inside of the same point. 哪一个? Oh, yeah, sure. So what should we call it? Oh, no. Actually, it's S1 as well, because it's just looping around. You just like, instead of one X1 here, then you twist the S1. Yeah, it's S1 S1. Okay, so the difference actually is the map here. Does it make sense? Okay. So here is Zn because you do it n times, you come back. Okay, you do it. Sorry. N. You do n time and then you come back. Okay. So next is why this terminology fit gone? I don't know what is it. I need to check it back. What I should put here. So a covering space is normal. Okay, if for every x and every pair of leaf, there is a deck transformation that take x prime to x prime to that, then we'll call it normal. 有啊，应该吧，不然的话干嘛做这个 definition 出来？ So actually you can check what is normal, what is not normal here. So for example, universal cover is normal. Okay. And then n-sheeted covering space is also normal. That's how, yeah, we get example, but normal, good. So out of these covering space, right? Okay. I have identified like 1, 2, 5, 6, 7, 8 is normal. So there's one thing is not normal. So maybe S3 here, S to 3, number 3. So 3 here is not normal. Can you see why is it not normal? So meaning there's one point, okay, such that there's a pair of leaf that you cannot send over using any that transformation. Can you identify? So you can see that there are at least two kind of A here, A kind of leaf here. So one of them is loop, the other two is not loop. Okay, so you cannot send a loop. So a deck transformation must send a loop to a loop, but the other two path is not a loop. Okay, you should check that. A 只是检查第一个点去哪里，第二个点去哪里，第三个点去哪里。Okay. Okay, and then see the rest. Okay, so far it's like that. Okay, good. So far so good. Normal and not normal. Okay, so maybe one thing you want to check lah. Okay, prove that a deck transformation send a loop to a loop. And maybe try and check this. Okay, send a loop to a loop. But then the other two paths are not loops. Okay, any questions so far? Okay, so let's see what we can do with this normal subgroup here. Normal covering space. So let's say we have a covering space, but both of the covering space and base space are path connected. And then we have this image subgroup of pi1 of x tilde. Then how to check? Why do we call these covering space a normal covering space? Exactly is when H is a normal subgroup. So we can talk about the normal covering space when the image subgroup of its pi1 is normal inside pi1. Okay, so this mesh up with group theory. So this is where the topology mesh with group theory. So if your image subgroup is normal, that means there is a deck transformation that sends every leaf to the other leaf for everyone. Okay, very strong one. And then moreover, we can compute. Okay, we can compute the deck transformation of x tilde here using nh and h. So nh here is what? Is the normalizer. Is it normalizer? Yeah, normalizer of h in pi1 x tilde. and the quotient by H. Okay, quotient by the image subgroup. Okay, so what did you see here? What did you see here? So H is something inside pi 1 of x, and H is also something inside pi of x. So your that transformation of S tilde, right, really coming from the pi 1 of x. Okay, your base actually determine what's your that transformation. Correct? For example, R. Just now we said that the Dex transformation of R is Z. This is it cannot be larger than the fundamental group of base space Z. So using that example, what can you think about is if this is a universal cover, then your H should be trivial. Your H is trivial, then it's just equal to the normalizer of your H. But I think everything normalizes, right? So the deck transformation of your universal cover should be the pi 1 of x. Okay. Does it make sense? Okay. But you see, for any universal cover, the deck transformation is just the pi 1 of x itself. Okay. For the rest, then you need to take pi 1 of x quotient by h if h is normal. Okay, if x tilde is normal. Because when x tilde is normal, h is a normal subgroup, then everything will normalize it. Okay, does it make sense? So the real work we need to do is this nh over h. The real work that we need to check is nh over h. And also normal covering implies normal subgroup and vice versa. Proof 不简单啊, actually not that hard. 哎，如果我讲 hard 不是 GG 啊，没有啊，开玩笑，真的没有这样 hard， 真的没有这样 hard 的我会跟你讲 hard 的会在 tutorial 里面，真正 hard 的会在 tutorial 里面。OK， 真的没有这样 hard， 你看就两面吧，呀，没有 hard， 不 hard。OK， 所以因为不 hard， 我们就让你自己去读了。OK。Yeah, but the main point is this, okay? Main point is this. This is the most general form. So how do you find the transformation of your covering space? You take the normalizer of your H, for H is the image subgroup, okay, of pi 1 of x, and then divide it by that subgroup. And then another thing you want to remember from here is normal covering space implies the image subgroup is normal. So this match up with the group theory normal. Okay. Is there any enlightening proof here? Not really. You just play around. Not really. Okay, maybe one thing you want to know is how do we make this quotient? Okay, how do we make this quotient? You need to build a map. Okay, so how to make a map from NH to GS tilde here? Okay, maybe this map is quite important. So what's this map here? Okay, so this map is this. So this map is not too hard of not. You just take an element in NH is a loop, and then this loop will define that transformation. That's it. 就是这样。Then 你要 determine 的是 what is the kernel inside this map， 就是同一个 idea 吧。One loop will move your pre-image. Okay, a loop will move your pre-image, and then you check its homomorphism. And then I think the more work you need to do is to check that what's the kernel inside here. Okay, And then you prove that the kernel is exactly H. Yeah. Any question on this? Not on the proof lah. Proof maybe you need to have a look. But any question on these facts here? 挺直接哈。
理解起来。
就是说这个 statement 是蛮 intuitive 的，我们想要的，但是要怎么去 prove 出来，你就要去 construct 那个 map， 等你就检查不了，它就检查不了，它不需要很长的 construction， 检查一下它就会出来。Okay, so I think the main idea here is how to link, again, how to link phi one of x to the deck transformation. But 就是刚才我们一开始讲的 idea， 下面那个 loop 会去移上面的 free image， 它会移动啊，它会移那些 leaf， 那些那个就是 idea 吧，就这个整个的 idea。And then yeah, okay. And then I think we almost done, but I think we almost done already. Almost. I mean almost. I think you won't need these in your assignment as well. Our assignment stop pretty early actually. I think quiz How about let's have quiz Let's stop here first. Okay, let's have quiz.
Okay.
这题目新鲜到都还没有写下来，没有，还是在我脑里面。Okay, let's do the quiz. Please turn off any electronic devices. Cut off any electronic signal. And keep all your books. Books obviously is prohibited.
反正电视就我看得到，
你把那书藏在你的脑里面就可以了。
然后买那个触控里面的。
数个里面。Okay. So first question is draw. Again, drawing. No need to copy question. Draw 4 covering spaces for x1 which x1. I think 这个照片出很多次了，在这个网上。Okay, draw 4个and then explain 不用 proof 了 explain briefly 就好 main point why are they covering space of x1 which is 就是重点要给我讲出来，你不用 build map 还是什么的，重点要讲出来。I think lecture note 也是这样子解释，其实没有 build 什么 map 给你看。Okay. Yeah.
大便，我真是服了。
用抄先拍完画掉。写一二，写一下第几题？
我以为它模型转了，它只要对应那个四方可以 OK 吗？
要讲答案呢？ 冷静，冷静。Yeah, please label A, B, so I can check your local homeomorphism. Don't just throw me the shell. Ask me to fill it in. You need to determine your local homeomorphism. When we started, just now，我们几点 start？感觉过了很久，还没有？我们写完了吗？还在写2分钟。 OK，姚一晨帮忙 shuffle 一下，我们快快讨论一下。shuffle 一下他们的，给他们改。OK，我们快点讨论一下，改一下。嗯，我叫多，I think so。感觉过很久了。我看到你们写到差不多停了。Okay. So if they draw any of these, you give them 2 marks each. Okay, if they have proper labeling. Okay, you give them 2 marks each. So
真的比这样
okay, so let's determine what's the 2 marks, another 2 marks you want to give. Okay, let's see. Sorry. 对。Let me see. Okay, so the key point here maybe is if they write something like sending all vertices to vertices of x, okay, and then x to x, that is a homeomorphism on the interior of the x preserved orientation. Okay, if they write this, you can give marks or something related to this, or if they write with orientation and each vertex such that the local picture near each vertex is the same as x, you also give full marks. Okay, either they write the top, this argument here, or they write the bottom argument here. Okay, these two you can give full marks. 什么？没有，一定要这样子。I mean like，那你觉得那个有提到这些东西吗？如果没有，你就给吧。哦，你自己本身你自己本身你自己本身的话我会看，不用紧。你现在先看你那张 paper，先看你那个人，你先决定一下那个人有没有对，别人会帮你决定你有没有对。你有机会，等我派回来的时候，你就有机会反驳现在是你去看别人的先。What？我觉得好像是identity 嘛，trivial 嘛，给他分了2分嘛，给他嘛，可以可以哪里？上面哪里？下面，因为我们有证过每一个 homeomorphism 是个 covering space 嘛，identity is a homeomorphism。什么？这上下其实是类似的 argument 来的，只是一个比较 formal，一个 less formal 吧。OK，so either 他们就是，the main point is every vertex 它的 local picture 要长得像下面那个飞飞的，然后它的 orientation 要 match 到，就是说，你看 B 就是来一个进一个出 ，A 一个进一个出，不可以来 A 两个进来 ，B 两个进来，这样就错了，这就是个 orientation。OK，就是他有写到这个东西就 OK 了。make sense？
因为我是多人的 graph，
不可以。报告什么来着？
两个进两个出就是多人的 graph
我不清楚你知不知道 oriented graph。OK，不要紧。
你写了，我
对，你先改这个人的先，然后我再决定你的，对不对？你觉得他 OK 就 OK。
这个比的存在我感觉。
OK，你先改你那个人先，等我派回来，你就可以看你的，对不对啊？哪一个上来一下？下面
变化
这个
开大，
你要哪里？
这个萝卜
上一下。呀，你先决定你那个人对不对就可以了。你有没有对，我会决定。喂。 有点紧张。啊，咋了？快点啊，我们还有1分钟，我们要出去啊。那个老师坐在那边，
对啊，对啊，
他已经做水果了，我们不可以给他做水果。OK，快点算一下分。一행帮忙收一下一행谁完了跟他收一下。
啊，不行，
我也不
来来来，给多少分？